Welcome back to Illusion Hashtag. Today we are stepping into the microscopic first lane. Imagine a high-speed bouncer who never misses a face and an elite detective who can spot a single suspect in a crowd of millions. This is Flow Cytometry Part 1. We are diving deep into fluidics, the laser, and the data that turn a messy biological sample into clear, actionable science. Strap in. It's time to meet that high-speed bouncer and the elite detective in the lab. Think about that for a moment. 10,000 cells, not in a minute, not in an hour, but every single second. In the time it takes you to blink, the flow cytometer has already interviewed a small city's worth of biological data. This is not about just speed, it's about precision. We are taking a chaotic sample and forcing it into a single file lane so our bouncer can scan each one individually. This massive throughput is what allows us to find that one in a million cell that could be the key to a breakthrough. So, what actually our ultimate microscopic bouncer doing at the door? It's managing three high-stake tasks simultaneously. First, counting. It is not just tallying numbers. It's processing massive heterogeneous population at a light speed. Second, examining. This is where it's get a bit personal. The system analyzes the exact physical and chemical vibe of every single cell that passes through. And finally, sorting. This is the FACS, fluorescence activated cell sorting at work. It physically separates the VIPs, which is typically our cell of interest, from the surrounding debris. Three step, one goal. Total clarity of what's in our sample. Now, to understand how this bouncer works so fast, we have to look under the hood. Flow cytometry operates on a three perfectly integrated tech stacks. First, there is fluidics. Think of this as the transport zone. It takes your chaotic cell suspension and uses thermodynamic focusing to inject them into a perfectly ordered single file line. Next, we hit the optics, the interrogation zone. Here, powerful laser illuminate each cells, while optical filters catch and direct the resulting light signals. Finally, the electronics. This is the translator. It converts the detected light photons into quantifiable digital signal that a computer and you can actually understand. It's a seamless handoff between liquid to light to logic. Let's break down the engineering of this hydrodynamic VIP light. To measure millions of cells accurately, they absolutely must pass through the laser one at a time. We start with the problem. A chaotic cluster mass of cells being injected into the central channel. If they stayed like this, the data would be useless noise. Here's the solution. The outer shell fluid. By surrounding the sample with this faster flowing fluid, we create a massive drag effect. And finally, the result. The flow front becomes parabolic. Because the velocity is highest at the very center, it squeezes those particles into a perfect single file stream. This is hydrodynamic focusing in action, the foundation of every piece of data we are about to collect. Now that we have established order, the real investigation begins. We have reached the interrogation point. After hydrodynamic focusing, our single cell finally step into the spotlight. A primary laser beam strikes it head on, triggering an instant burst of optical data. This is not just a pretty light show. Every angle that light bounces, whether it's reflecting off the surface or refracting through the internal organelles, tells a story about that specific cell's identity. This is the exact moment where physical matter is translated into raw information. Now, the interrogation is happening. But what exactly are we reading? When that laser hits, the light scatters into what we call the scatter matrix. To extract the truth about a cell, we measure these lights at two distinct angles. First, we have forward scatter or FAC. This light travels in the same direction as the laser. Think of this as the scale. It indicates the relative size of the cell. If it's a large, healthy cell, the FAC signal is strong. If it's small or dying, the signal drops. Then, at a sharp 90-degree angle, we have side scatter or SSC. This is measured perpendicular to the beam and acts like an X-ray for granularity. It tells us about the internal complexity, the granules, the nucleus shape, or the vacuole hidden inside. Size and complexity. With just these two dimensions, our detective can already tell a lymphocyte from a granulocyte without even breaking the sweat. Let's zoom in on the forward scatter. Think of FAC as the silhouette. When the primary laser beam hits the cell, some of that light is scattered in the exact same direction it was traveling. A photodiode, positioned directly in line with the beams, is waiting to catch it. This measurement gives us the relative size. Just like a larger object casts a bigger shadow, a larger cell scatters more light. Mathematically, the area of that silhouette is proportional to the square of the diameter. So, even a small change in the cell size creates a detectable difference in the signal. Our detective now knows exactly how big the suspect is before they even look inside. Now, if FSC is the silhouette, then the side scatter or SSC is the X-ray. While sunlight passes straight through, other photon strikes the cell's internal structure and bounces off at a 90-degree angle. This is not just a shadow anymore. It is a detailed look at the cell's internal complexity. Because these scattered signals are much weaker than the primary beam, they are caught by photomultiplier tubes. These are ultra sensitive detectors designed to amplify even the finest whisper of light. Every granules, every fold in the nucleus, and every vacuoles add to this signal. The more clutter inside the cell, the higher the side scatter. Our allied detective now knows the size and the internal content of the suspect. The profile is almost complete. Now, let's log these two truths in side by side. On the left, we have forward scatter. Since it measures at 0 degree, directly in line with the laser, it's our primary metric for relative size. Bigger cells cast larger shadows, resulting in a higher FSC signal. Keep this in mind for your data analysis. Dead cells often show a significantly low FSC. On the right, we have side scatter. By measuring the light at a perpendicular 90-degree angle, we are looking at the internal complexity and granularity. We have talking granules, vacuoles, and lobed nuclei. The rule of thumb here is simple. More internal structure lead to more scattered light, gives you a higher SSC signal. Size versus complexity. This is how the scatter matrix begin to reveal the hidden identity of every single cell in that 10,000 per second stream. Once the light scatters, it's not just a single beam anymore. It is a chaotic rainbow of data. To make sense of it, we use signal routing, also known as optical sieve. Imagine a maze of diachromic mirrors on and optical filters acting like molecular coin sorters. They bounce or allow specific wavelengths to pass through, ensuring each photon hits the correct detector. First, we have the long pass filter. These are the gatekeepers that only let light equals to or greater than a specific wavelength to pass through, like LP500, letting everything 500 nanometers and up through. Then we have short pass, SP500. It is the exact opposite. It only lets the tight short waves through and sends the long ones packing. But the most exclusive gate is the band pass, BP500 by 50. This is the ultimate VIP list. It transmits exact wavelength between 480 and 520 nanometers. If you are not in that precise range, you are out. Remember the golden rule. Dichromic mirror route the light, while filters block the noise. This team up is what gives us the crystal clear data we need. Physical scatter is great, but it only tells the half of the story. To truly crack the case and identify specific cell types, like separating two lymphocytes that looks identical on the outside, we need to go deeper. We need to tag the invisible. Sometimes size and complexity just are not enough to identify our target. That's when we go looking for the VIPs. To do this, we use fluorescent dyes conjugated to a monoclonal antibodies. Think of these as glowing name tags. They are engineered to ignore the crowd and bind only to specific individual antigenic surface marker, like the well-known CD4 or internal molecules that defines a cell's secret identity. When our primary lasers strike this tag or fluorochromes, things get interesting. An electron jumps to a higher energy level, then quickly decays back down. In that split second, it emits excess energy as a photon of light. In the sea of millions of cells, these glowing tags act as a beacon. They tell our allied detective exactly who is who, allowing us to pick out the rare important players from a massive population of otherwise identical looking cells. This is how we move from just observing a sample to truly decoding its more specific secret. We have filtered the light, but the computer cannot read photons. We need the electronic translators. These detectors convert light signals into processable electronic pulses. For the loudest, clearest signals, primarily forward scattered, the machine uses photodiodes. These are less sensitive, but they're perfect for handling the high intensity lights that defines a cell silhouette. But for the whispers, those faint weak signals from the side scatter or specific fluorescence emission, we need the photomultiplier tubes or PMTs. These are highly sensitive signal multipliers. They catch a tiny photon and run through an amplifier, turning a barely there signal into a quantifiable digital wave. From a physical cell to a flash of light, and finally to an electronic pulse. The investigation is complete and the data is ready for the detective stage. Before I move any further, let's look at the master workflow. This is where the three tech stacks, fluidics, optics, and electronics, dance together in a perfect synchronity. It starts here. The fluidic nozzles creating that high pressure single file stream. Then the laser strikes. In that microsecond of interrogation, light is scattered and fluorescence emitted. Our optical sieve of dichromic mirrors and filters instantly routes these signals to the FSC, SSC, and EMT detectors. Finally, the electronic translator sends a digital pulse to the computer, transforming a living cell into a data point on your scatter plot. This loop repeats 10,000 times every single second. Now that we have decoded the hardware and the physics, we are ready to see what happens when the bouncer actually starts sorting the crowd. Thanks for watching. We just cracked the basic of FACS, how cells flow, how lasers hit, how fluorescence glows, and how all that biological chaos turned into clean readable data. Basically, we taught machines how to understand cells. Pretty wild, right? But hold on, this is only part 1. In part 2, we are going full deep dive mode, real facts workflow breakdown. So, if you are trying to level up from I kinda get facts to I can actually analyze this stuff, hit subscribe and turn on notification so you don't miss the next upload. I am the lead at Illusion hashtag. Thanks for vibing with us on this microscopic adventure into the technology of life. Stay curious, stay analytical. See you in part 2.